Yeah, thank you, Randy. Hopefully you can hear me, and I think you're seeing my screen now. That's a great introduction, and I enjoyed meeting you back there. So I know many of you in Central Region, and you probably know my name from a different context. For the last several years, have been a lead forecaster at the Weather Prediction Center. And so Randy and I worked together on the flash flood experiment one year when you were still out in Salt Lake, and that really gave me some better perspective on Western flash flood events. That was nice. I joined the NSSL and War on Forecast team late last year, and my title is program lead, which sounds impressive, but really there's just dozens of people here that work on WoFS, and it's been remarkable to see the enthusiasm both here and of the end users, particularly in southern region, but we're branching out a lot more in central and eastern region now as well. So we have some great things to show you today, and I think you really enjoy the talk. Basically, it's a really unique model system, and it's groundbreaking in many ways. So I think that's worth repeating sometimes. That you really it needs to be viewed in a different context than just the next great CAM to come along. So we'll give a refresher. Pat Skinner will do that, showing you some ways to think about WoFS output and how to apply it. I'll show some real-world examples from last year and talk about our experiment plans for this year. And then Katie's going to help us with pointing to some other WoFS resources towards the end of the talk here. And like I said, just kind of reminding ourselves of the context of what this effort is all about. It really started over a decade ago with a grand vision in recognizing that where we've come from in the warning paradigm in weather forecast offices is that you get to this point within an hour or two of an event where you're just completely driven by observations and largely by the radar observations, particularly for drawing up polygons. And it's all deterministic based polygons. And so we decided here at the lab, over 10 years ago, that convection allowing models had matured enough to allow us to do something more innovative and provide finally some objective guidance and some probabilistic guidance in that warning kind of time frame within a couple hours of an event. And so because that's a strategic goal at NOAA to increase this, especially tornado warning lead time, which has really plateaued, this was the idea that can we do this? Can we design a tool to help forecasters in that space that's largely driven by observations without any objective guidance? So that's kind of the motivation behind what we've done with WoFS. And so with that, I think we have Pat Skinner on, so I'm going to hand it over to you to kind of talk about what WoFS is and how to use it.
All right, thank you, Patrick. Can everyone hear me?
I hear you.
I think that is a yes. Okay, good. Yeah, thank you for that introduction. And as you mentioned, that WoFS is really pretty dramatically different than other CAMs and CAM ensembles. So it is still a CAM ensemble, but I'm going to try to talk about why it's different and what makes it different, and then also how does the guidance differ and how do you interpret that guidance. So the main reason why it's different is because it's been designed to make a different kind of forecast, which Patrick alluded to, which is there's this gap in guidance you get for severe weather, where it's illustrated here in the figures on the left and right, where as a tornado watch is something that covers a regional threat area for several hours, up to 6-8 hours in time. And then there's no official products that are issued between that time and a warning, which is, for a tornado warning, that's valid for typically about 30 minutes and covers something that's sub-county or a very small local area. And it's also specific to an individual thunderstorm. So our goal with the War on Forecast system is to be able to provide numerical weather prediction guidance and give probabilistic guidance on what are the hazards likely within individual thunderstorms between the watch and the warning scale. And if you go to the next slide, Patrick, this is just an example of that for this case, where you're now looking at a 6-hour forecast of the WoFS likelihood of updraft velocity exceeding 60 meters squared per second squared in the 2 to 5 kilometer layer. And that's really just a proxy for mesocyclone occurrence. So we're looking at the probability of a mesocyclone occurring anywhere during this time during a 6-hour period. So it covers about the temporal period of a watch. But you can see that you're getting storm-specific guidance, so that you can see the individual storm tracks and the likelihood that they're going to be supercellular during that period. And that's the kind of thing that we're aiming for. And if we go to the next slide, I just some brief overview of some of the configuration of WoFS. And really, it doesn't sound like much, but what sets WoFS apart from other CAM ensembles is the rapidly cycled assimilation of remotely sensed observations. So systems like the HER will assimilate radar data and satellite data every hour. However, we do it every 15 minutes, which is effectively 4 times the amount of data per hour. And what that does is that allows WoFS to accurately initialize individual thunderstorms within the model domain. And the basic principle is that if we're able to accurately initialize these thunderstorms in the different ensemble members, then we'll be able to issue an accurate short-term prediction of their intensity and evolution. And so we do this by every 15 minutes we assimilate MRMS gridded reflectivity values and also straight gridded radial velocity observations from every WSR 88D in the WoFS domain. We typically use a 900 kilometer by 900 kilometer square domain, and we issue that on demand sense. So you can plop it down anywhere in the country, anywhere that the HER runs, which is what we're initialized from. And then also GOES cloud water path. And then when available, the OK mesonet, but obviously we're not going to be getting that in cases that are not in Oklahoma. So really these radar and satellite observations should allow us to accurately initialize the individual thunderstorms. And once we've done that, we begin issuing 18-member ensemble forecasts. Depending on the configuration, we launch that either once or twice an hour, and with up to 6 hours of lead time. Another novel aspect of this is we output the forecast. We have forecast output available every 5 minutes. So you don't have to look at the hourly swaths. You can get some of that sub-hourly evolution in storms. And then we've tested a lot of different visualization tools, because this is a lot of data, a lot of probabilistic products to throw at you, and tried to come up with some easy to use visualizations that are available through a web viewer, which we'll look at a little bit later. And so if we go to the next slide, I wanted to just show 1 or 2 examples of what WoFS data look like and what are some quirks to interpreting that data. So in this case, if you start with the right panel, that's the truth in this case. This is MRMS composite reflectivity that's been gridded to the WoFS domain. And as you can see, you have a line of thunderstorms in southwest Kansas, and then you have developing convection along a dry line, in this case, near the Oklahoma-Texas Panhandle border. And then in the middle panel, you see what does the 0-minute forecast or the analysis of this event look like in a single WoFS member. And it's definitely not perfect. There's convection, in central Oklahoma that doesn't exist in reality. And some of the locations and shapes of the storms are off from reality. But in general, most of the storms, especially within the line of storms, you have the strongest reflectivity values are coincident in space and generally in shape and intensity with the MRMS values. And so that's what we're going for, is we want to accurately initialize these storms within the different members. And similarly with the convection in the northern part of the dryline convection, but if you look at the area highlighted in the red box, that's an area of recent convection initiation, you see that you have much weaker returns in the WoFS member 3 composite reflectivity. And that's exacerbated. That's consistent across all the different WoFS members. If you look at the left panel now, this is now the probability of exceeding 40 dBz in the ensemble. And you can see that it's very high. These deep reds indicate all 18 members are basically predicting over 40 dBz in the locations of most of the observed storms, except for these developing storms on the southern end of the dry line. And what's happening there is that they recently initiated, and so WoFS has not been able to assimilate many observations of their existence into the system. So it has not been able to spin them up within the model initial conditions. And that illustrates, I think, one of the important concepts of interpreting WoFS guidance, which is the quality of the guidance and the forecast is going to be determined largely by the quality of the initial condition, which is in turn determined by the number of observations you've been able to assimilate of a given individual thunderstorm. So you're going to have variable quality of forecasts across different storms within the same domain and the same forecast. So it's important to recognize, look at the analysis and recognize which storms does WoFS seem to have a good handle on and which storms is it not accurately initialized yet, or does it not seem to be initializing well? And that should help give you confidence about which of the storms in the predictions of WoFS are going to be more likely to occur rather than not. If we go to the next one, I was going to look at, so that's the analysis. I was going to look at how this varies during the forecast. And, you know, one thing that's interesting about WoFS is we primarily use it to predict, we use it heavy rainfall and severe thunderstorms. I'm going to focus on the severe thunderstorm side here. And these are discrete events. We're not predicting, we can predict CAPE and temperature and things like that that are continuous, but we're primarily predicting discrete rare events. Even though there's, you know, pretty widespread storms here, it's covering well under half of the domain. And what happens in the forecast is you have these storms that are predicted in generally the same locations in different ensemble members, but with increasing spatial spread as you get longer forecast lead times. And when you use a product like the ensemble mean, that's going to wash out the values, the intense values of the convective storms, and give the sense that it's storms are weakening or becoming stratiform. And if we go to the next slide, that'll show an example of that, where the individual member is showing really intense, likely supercellular storms in western Oklahoma here. But if you look at the ensemble mean reflectivity, you know, it looks like weakening rain showers are moving into western Oklahoma, which is not at all representative of what the individual members are predicting. So that's one reason we don't recommend using ensemble means for discrete fields. And if you go to the next slide, one thing we found is useful is something that would be akin to a spaghetti plot on a medium range model, but it's just a paintball plot where you plot a limited amount of information from each ensemble member on the same plot. And so here you can see a loop of these paintballs, which gives you a sense of where the thunderstorms are in this forecast in each member and how they evolve. And I think there's a lot of neat information there. This is a good go-to product to just get a brief general sense of what WoFS is predicting. As you can see, at least a rough measure of likelihood by how much the paintballs overlap. You can definitely see differential storm motion. There's some left movers mixed in there, and you can look at some different sizes. You can see maybe one member trying to go upscale in western Oklahoma, but many others predicting, you know, relatively large storms that seem to be moving to the right of the other storms. So you get a sense that they are predicting right-moving supercells in the region. So there's a lot of information in just looking at a loop of the paintball plots. And then another thing I wanted to mention about interpretation of WoFS guidance is it's important to use the probabilistic measures in tandem. And primarily we have products that measure the likelihood of an event occurring, and that's just the probability of exceedance. So probability of rainfall greater than 1 inch, or probability of updraft velocity greater than 60 meters squared per second squared, something like that. But you could also slice the CDF of the of the ensemble in a different way and get a measure of intensity, where you look at, you know, what value is 90% of the ensemble members predicting a value lower than that number. In that case, you get a measure of intensity, so a reasonable worst case scenario for intensity. And this is an example from later in the day that we were just looking, where if you look at the probability of occurrence, you have clearly 3 supercell tracks going into western Oklahoma. The northern 2 tracks have a very high likelihood of occurring, at least of having a mesocyclone associated with them. The southern track is a little more uncertain, and maybe 40–50% likelihood. That's what those light kind of pink colors correspond to. However, if you look at the intensity values, you notice that it's a very different story, where you have weak intensity values with the northern track, strong intensity with both the southern 2 tracks. So you have a situation where you have a high probability of low potential severity event in the northern track, a high probability high potential severity event in the central track, and then a low probability or moderate probability high potential severity track on the southern one. And just for reference, those purple colors and the updraft velocity are getting up over 500 meters squared per second squared. So you have you know, large intense mesocyclones being predicted in at least a couple of the members. And so if we go to the next slide, just trying to summarize some of this, I guess, tips really, or considerations for interpreting WoFS guidance. The main one, I think, is just recognizing which storms does WoFS have an accurate initialization for. And something I didn't mention, but is also is that, you know, how accurate does the environmental conditions look? Because typically WoFS forecasts are most accurate when it has an accurate storm scale initialization, but also an accurate initialization or forecast of the upstream mesoscale environment. So if those look good, then you can have more confidence in the storm scale evolutions being predicted by WoFS. However, if a storm is just initialized, it's likely going to be a lot more uncertain as to the track and size and evolution of that storm. And so that's a time where you'll see larger changes as you go from successive WoFS initializations to the other. When you're looking at a discrete field like updraft velocity or reflectivity, I'd say avoid the ensemble mean, and to a lesser extent avoid the probability match mean, because that can give unphysical representations. And the probabilistic measures and also paintball measures or the member viewer are really good for looking at that. And finally, for probabilistic information, using the probability of exceedance and also the percentile products in tandem helps to give you a fuller picture of both the likelihood and severity that the ensemble is predicting for an event. So I think that's all I have on that subject. So I'm going to turn it back to Patrick, and he's going to show you some specific examples.
Yeah, thanks, Patrick. That really sets me up nicely. And I know, as a forecaster, just seeing a new tool in action over a number of cases is one of the great ways to build confidence in its ability. So I've started to dig through the cases that we saw just last year. We've got about 3 years of really good data now on this current configuration of WoFS, and we'll be running it again this year. So there's a lot to look at. And I like this particular case from South Carolina because you have it's a well-defined supercell out ahead of the main action there. So it's something you can easily kind of track over time. So you're looking at the observations on the left-hand side. This supercell persisted for over 5 hours, and I'm just showing 2 or 3 hours of the track here, but had many very large hail reports, kind of unusual for that part of the country, and a few tornadoes, with one of them being an EF2. And so on the right-hand side, I've got a WoFS image. And part of the thinking here, and I think the main point of this talk, I think, is how do we, we're still grappling with how do we use this great new tool in operations. It's not just one thing. It's not just the ensemble mean. It's the member forecast. It's the probabilities and percentiles. And so we need to find efficient ways to mine that data in an operational sense and be able to apply it. And many of the visualizations, which I think are one of the strengths of WoFS, having been developed over time in the test bed, getting feedback from NWS forecasters. Many of these visualizations do combine 2 or 3 different products in one. So on the right-hand side here, you're seeing an accumulation of swaths of those probabilities, like Pat just showed for the Oklahoma case, the probability of mid-level updraft rotation. And there's very clear signal of a high probability there across northern South Carolina. And one thing Patty didn't mention is that you can choose different neighborhood ranges. So this is actually tightening in on a 9-kilometer neighborhood. So you would use that in a case where you have higher confidence that you're well initialized, that you're looking at an individual cell, and then you can zoom out and use larger neighborhoods if there's more uncertainty to at least get a sense of what all is possible. But in this particular case, it's a well-defined supercell, and even in the ensemble mean, which is the gray contours there of reflectivity, we see what pretty much looks like a long-lived supercell. So the question then is, how could a forecaster use this information? And of course, the vision back from 2009 is that eventually, maybe it will be so good that you can use this kind of thing to issue a polygon warning. But I think until we get to there, perhaps this just lends some confidence to forecasters at a WFO to act a little bit earlier, to make a phone call to an emergency manager downstream, something like that. And certainly seeing consistency in the runs is one way to gain that confidence. And so I've put together this slide here looking at 3 different consecutive runs of WoFS, and I've plotted 2 of the tornado locations that occurred within a half hour of each other there in the yellow and red X's. And at 2255Z, all these images show in the ensemble mean what looks like a big nasty storm bearing down on the location of that EF2 tornado with a really high probability of being a rotating storm. And so if you were to use this information, from the first run over on the left-hand side, that's greater than 2 hours lead time to that EF2. And this Sioux at Columbia, South Carolina, has told us that they were using WoFS that day in operations, and pretty much did use it in that fashion of giving folks a heads up, maybe putting more specific language into a short-term forecast or a special weather statement So we're not seeing that direct connection to a polygon necessarily yet, but there are other ways that WoFS is beginning to influence warning operations. And I like this next example because it really shows the value of the probabilistic nature of WoFS and using that to dig deeper and look for more information. So picture yourself on the night of the Nashville tornado outbreak from March of last year. And here we are early in the event, so there has not been a significant tornado as of yet. There were a couple of weak spin-ups in Kentucky at this point in time. But you know, if we're looking to kind of go left to right as a forecast process here, the way that I've structured this slide. So we're thinking about tornadoes. We might pull up the strong tornado or significant tornado parameter, STP, and we see a pretty healthy area of values of 2 to 3 there over Western Tennessee. And this is something that I've seen consistently in the tornado events within WoFS, is this corridor of enhanced STP. But in the ensemble mean reflectivity, there we see the squall line or more linear looking convection across Kentucky, and then nothing in this location that an hour from now is going to see an EF1 tornado at Idlewild, Tennessee. But if we dig into the probability field over on the right-hand side, this is probability of reflectivity greater than 40 dBz. We see that there actually is a 60% chance of a cell being there. So that might prompt me as a forecaster then to check out the individual members. And I've plucked one image there in the inset. You'll see WoFS member number 4 has a cell that looks you know, threatening in that kind of an environment with high STP. And so just having this information might inform a forecaster to then be a little bit quicker on the trigger once things start to develop. And then as a flash flood forecaster at WPC, you know, we actually, there's been a 2-year running project with WPC to do summertime runs of WoFS for flash flood events. And we had a really intriguing event last August where a thunderstorm cluster formed and persisted for about 4 hours over Leesburg, Virginia, resulted in 5 inches of rain and a flash flood emergency. And this is so typical of flash flood forecasting in the summer, where the biggest, most impactful event of the day ends up being a small cluster of storms on a county scale, well outside of the main event, which was this large MCS with a lot of wind and hail over central Virginia. And so it was really impressive to see this loop of QPF from WoFS and from the ensemble mean of reflectivity there, which formed a storm and held it stationary for a good 4-hour time frame. And that's not performance that I'm accustomed to seeing from any model system to hold a cell in place on that kind of a small scale without it raining out or propagating in some direction. So that's, to me, pretty impressive. And there's little crosshairs there that shows the heaviest rain in the entire domain from this particular run occurred right there at Leesburg. And Steve Zubrick, who's the SU over at Sterling, Virginia, said, yeah, they were using WoFS in real time and communicating that information to the emergency managers there in advance of the flash flood emergency. And this was a good hour and a half prior to the event. So it's really encouraging that we're seeing some good performance like this in the 1 to 2 hour lead time frame and finding ways to apply that information. And I know that, you know, Pat emphasized the need to synthesize observations and really initialize each storm. But I'm finding too that just the emphasis on high resolution storm scale modeling may have led to some other benefits. You know, in this case, the storm hadn't even initialized, or it hadn't even, you had not had convective initiation as of 23Z at the time of this WoFS run, but the model itself was able to initiate the storm and then hold it in place. So I thought that was a pretty impressive case. And that did find its way into a WPC product, a mesoscale discussion. There are other examples here of how WoFS has influenced category upgrades from SPC on a small scale, or Graphicast from a WFO, highlighting a hail threat. And then there are probably many other applications that we're just starting to discover, because this really is a brand new technology. We saw last year cases in the Southern Plains of damaging winds from evaporative cooling when you had a decaying system or a wake low, and that WFOs here were able to pick up on that signal ahead of time, provide some lead time on wind. We saw a case where a storm was developing in the model just as it was reaching Oklahoma City at the tail end of this line, again, the lower right-hand side of this image here. And so the WFO was able to message increased opportunity for large hail with that storm. And then we did a special run of the model for the Iowa derecho and found that there may be advantages to this kind of rapid data assimilation even out farther in lead time, where the model was able to better diagnose that storms in Nebraska would not grow upscale overnight, and therefore leaving the environment more pristine for the derecho that eventually occurred hours later. So lots of exciting potential here, and we hope that you'll help us discover some of these applications. So I just want to point out a couple of cool things on the web viewer that you may not know about. The member viewer that we've been mentioning a couple of times here, you can find that under the radar satellite menu to be able to look at reflectivity from individual members. There are some verification tools. If you look, there's a tab there on the right-hand side. There's also a scorecard that was developed last year that will compare domain-based statistics for WoFS to other ensembles like href. And something I didn't know about until I got here to NSSL, that there actually are soundings, forecast soundings from the model. And so you're seeing the little dots here over the image. So if you toggle that on, you can actually get forecast soundings. And there are a few other things that'll be coming this year. We're integrating, we have one individual member that's at a higher resolution. It's 1.5 kilometer deterministic forecast. This is kind of being run separate from the main ensemble, but we're going to plug it in there as one of the members in the member viewer. So please check that out. And there'll be some other interactive capabilities that we're kind of working at under the hood right now, but should be coming along this spring. And so I'll just emphasize that for this year, make the most of April and May, especially. We'll be running daily on the weekdays in May and the first week of June there for the spring forecasting experiment at our test bed. We'll be running as much as we can during April for targeted weather events. But this summer, we don't have any funded projects like we have the last couple of years at WPC. And this is a good time for us to catch up on supercomputer maintenance and on analyzing all the great data that we've collected over the last few years. There's also a pretty big shift in modeling with the arrival of FV3, and the attempts to integrate that into WoFS will be important for our ability to get the current system into operations over the next several years. So we really need to focus our effort on that. But there is a possibility of some cloud-based runs that would not require the supercomputer that could complement our activities this summer and give us some opportunity to run on the more interesting days. So with that, I don't want to run too long here. I want to hand it over to Katie, and she's going to give you some other resources.
All right, thank you, Patrick. Just a few quick things from me to wrap up this talk. The next slide, if you could go along, thanks, Patrick. One thing I want to share is something we've been doing this year in February, March, and we'll be finishing up at the end of this month, is a virtual testbed experiment with a group of local weather forecast offices, WPC and SPC. We've seen utility in real time for WoFS guidance for each of these different offices. And so we've been trying to learn about how WoFS can be used across the forecast process that spans national center and local office responsibilities. And so we're soliciting feedback through the testbed mechanism, but we also really appreciate real-time feedback. We want to know how it's being used in offices. And so on the next slide, You can see that we've got the graphic here of the interface, which Patrick was just going over. And on the right-hand side, you can see this green box, and it says NWS forecaster feedback. And so if you use the guidance in real time, we would love it if you would click on this link and provide feedback. We've made it really short so that it's not too tiring at the end of the shift, because we know that can be a tedious task to do when you just want to go home. But it should just be 5-minute feedback, and we'd like to know who's using the guidance, when you used it, so for what event, what products were you using, and what was the impact. So just some very high level kind of bullet point information. And we also like to take suggestions. So if there's something about the interface or the way that the products are designed, and you would like to make suggestions for improvements or to see something new, you can do that in this feedback form. And we have seen examples of suggestions that have been implemented during the same season. So we try to take what you suggest to heart and implement them, and hopefully see improvements that you deem would be useful. Okay, so that's the real-time feedback. In terms of training, we know that training is important. It's something that things like this webinar is helpful for priming forecasters for using the guidance. But if you want to do some training or familiarization on your own time, there are a couple of resources to do that. One is the WoFS viewer video overview. This was actually put together by an NWS forecaster, Matthew Day, from the Norman Forecast Office. He went ahead and put together this 10-minute YouTube video. And it's a really nice overview of how to navigate the website, the kind of products that are useful. He gives some really nice explanations of how to interpret and make sense of the products. So that is a definite go-to, especially if this is your first time using the guidance and you just kind of want to get spun up quickly. We also have some more in-depth resources. This was something that we actually created for one of the spring forecasting experiments, and we have shared with some of our collaborators at different offices previously also. This is by no means final format training. We intend to kind of improve and have finalized training when WoFS goes officially operational, but these resources are very useful. The one on the left is what is one forecast, so it's more of a programmatic overview of what the program is, what the system does, how it's different to other CAM ensembles, what the concept of operations looks like. And then the one on the right, understanding one-off forecast guidance, this training goes through more of the concepts. So things like Pat Skinner was talking about how to interpret probabilities and percentiles and combining concepts. So more about the interpretation of the guidance. And so those links are there. Feel free to jot those down. You can always email and reach out if you want to grab those links at a later date. But they are available online for you to go and use at your own pace. Okay, and then I think for the final slide from me, getting WoFS run updates. Forecasters often want to know, well, how am I going to know when WoFS is running and if it's running over my CWA? Well, one thing you can do is sign up for the daily status email list. The way to do this is to email Brian Mattia. His email address is right there. Just let him know you would like to be added to the list, and each day that WoFS is running, a daily status email goes out and you will receive that. An alternative is to follow the NOAA NSSL and the NOAA HWT Twitter pages. We're planning to provide updates each day WoFS is running via these existing Twitter pages. So go ahead and follow that, and that would be a nice, easy kind of public announcement for getting that information out. Okay, I think that wraps up all of the content from this presentation. So thank you, and we'll hand back to Randy and Ryan for questions.